As you all demonstrated this morning with the network overload, we live in an era of big data, and that's why you're all here, because we're all thinking about machine learning and its applications in, data science industry, everything you witness out there on your iPhone, on Amazon, and Facebook, everything, all of our technological sort of infrastructure is being, as you know, changed drastically by machine learning. And what we're here today and this week to talk about is basically how this same revolution in machine learning is affecting our study of quantum physics and many-body physics, statistical mechanics, and condensed matter, and so on. So, before I start, just a few sort of organizational things. As I wrote on the boards in both rooms, there's several sort of platforms we'll be using for the school. The Slack workspace is your conduit to talk not only to us, your instructors, but also to each other. So there's channels on there. There's peer-to-peer direct messaging that you can do, and so on. So the first thing I encourage everyone to look at is the software installation channel to start getting yourself ready for the tutorial that will start later this morning. That'll involve getting your Python installed by, like I say, a couple hours from now. Use Python 3, I think it's 3.7 is the latest. Definitely has to be Python 3. GitHub, if you're not familiar with GitHub, I encourage you to look on this GitHub page, and our tutorials for today and for the rest of the week will be under this repository name here. And so you can either clone a repo if you know how to use Git, or you can download a gzip file, which will have all the tutorials and so on. We might update these as the week goes on, so we'll tell you whether or not you have to update the repository as we go. For tomorrow, you'll need TensorFlow when we start the real machine learning part of the program. So there's a PDF provided in the tutorials, so I encourage you to look at that today. Okay. So today what we're doing is reviewing in lightning fast speed everything you need to know in statistical mechanics and quantum physics for the rest of the week. And we're going to frame this discussion sort of in the context of machine learning and big data. And as I mentioned, machine learning has advanced very rapidly, and it's particularly useful for us in terms of its ability to make predictions on big data. So you start with what I'm going to call big data and make predictions. That data could be anything that you generate, any of your sort of texts that you're sending over Slack workspace. It could be all of your photos that you're uploading, any of the videos that you're watching online. That's the era of big data, and that's where machine learning really thrives. I want us to start thinking about an analogy between statistical physics and the data that we might encounter in something like an image. So imagine an image that's made up of some pixels. I want us to think of black and white pixels. Each one of these squares is either a 0 or 1. It's a black or a white. And as you know, because you're used to digital photography, if you look at a certain pixel arrangement, you can often interpret that as something like a picture of, say, for example, a cat. So we're going to use this sort of idea of pixels, a certain number of pixels. I can take values, and the idea that we can form a prediction based on just this raw data that's contained in these pixels as the analogy as we move forward into statistical physics. Okay, so here's the data, and here's one of the predictions. Obviously that doesn't look very much like a cat, but I want you to imagine the size of photo that you may have on your hard drive or on your camera. Imagine the amount of pixels associated with that image, and try to imagine in your mind, a computational program that would take you from all of those raw values of those pixels into some sort of predictive encounter with them. In many-body physics, which is a term I use for any sort of physics of many particles that interact with each other in a sort of non-trivial way. So in our field, this could be condensed matter, could be quantum information, and in this class we'll typically take the perspective of statistical mechanical systems. In condensed matter, the pixels of an image might be, say, for example, the electrons in a solid, talking and interacting with each other with the laws of quantum mechanics. In quantum information systems, like a quantum computer, the equivalent of these pixels might be the qubits. And in statistical mechanics, which is sort of, I'd say the simplest way that we can approach a lot of these many-body problems, I will take the interpretation of the many-body problem as being many interacting sort of classical spins. Okay, so let's just say Ising spins. There may be many more applications. You might have some in mind as physicists. You might be thinking of cold atomic systems, or you might be thinking of electron transport, or all sorts of different stuff. One of the common themes that we'll use in this class is the theme of interacting Ising spins. The tutorial today will be an Ising model, which is binary units, binary spins, which can be black, white, plus, minus, up, down, whatever you want to label them, interacting according to some Hamiltonian. So the task in many-body physics is often the same as the task that we encounter in machine learning applications. That's taken this microscopic data, maybe the positions of an electron, or the state of a qubit, or the state of a magnetic spin. Can we make predictions on that microscopic ensemble? Can we determine, not just the label of sort of the, cat versus dog, which we'll describe as labeling a phase of matter, but perhaps also predicting some time series, or some spatial series, some correlation functions. We'll be interested in the underlying probabilistic or statistical description of these systems. We'll want to use generative modeling and other unsupervised learning techniques to reconstruct the state that underlies these microscopic images and so on. So we're going to have lots of tasks for predictions in many-body systems that we'll encounter during the week. So supervised learning. We'll talk about neural networks. Unsupervised learning with generative modeling. And more. So as the week goes on, we will discuss sort of more and more, I think, complex scenarios for machine learning for these many-body physics problems. So what is big data in many-body physics? We're going to encounter quite often the idea of sort of intractable problems, which may be some things like calculating the expectation values of observables, like I'll talk about. And it's sort of fun to quantify what this means. And if you're familiar with quantum mechanics, you're familiar with the concept of a Hilbert space. And this will be the unifying concept that we'll discuss throughout this week. So the idea of the Hilbert space of quantum mechanics, which we can also describe in the classical limit, as I'll discuss, is really the ultimate big data. And that's why machine learning techniques, which are used to very large images, very large videos, many, many pixels, lots of natural language processing, this idea of big data is the reason why this technology is transferring so nicely into the realm of many-body physics. So for example, if I have a qubit, just some numbers to keep in mind. So in the sigma z or computational basis, I can imagine that my qubit can have two states. That's the size of the local Hilbert space. So that's one qubit. If I have n qubits, the size of the Hilbert space, which is the size of all possible, the space of all possible images that are made up of those eigen, say, vectors in sigma z, is this number 2 to the n. So it's an exponentially large number. The fact that it's exponential is very important because it makes certain problems intractable with sort of traditional computational algorithms. Okay? How big is this number? We're going to discuss the two-dimensional Ising model in our tutorials, which is sort of the classical analog of a qubit system. So if I have a two-dimensional Ising model, you'll construct lattices where each, if you will, classical bit lies on the vertex of a lattice. So think of an image formed by these two sigma z states. You'll routinely be able to solve, using this Monte Carlo technique that we'll develop, sort of lattices of the size of 8 by 8, which is 64 qubits. That number 2 to the 64, which I encourage you to calculate, did I write it down? I think it's about 10 to the 19. If you tried to store that Hilbert space, so if the state space of all possible images formed by binary variables on that size of lattice, that number is greater than all the data storage capability of the entire Earth. It's bigger than the entire internet. That includes the surface net and the dark web. So let's just say bigger than the internet. That's what we mean by big data in the context of these many-body systems. The state space, this space of images that are possible on just an 8 by 8 sort of classical binary system is exponentially large. This number is fun. If you thought of a 16 by 16 lattice, 2 to the 264, 265, 256 probably. Oh. 256. This, I don't know right off the top of my head, it's something like 10 to the 77, 10 to the 80. This is greater than all particles in the entire universe. Bigger than the universe. So you can see that the complexity associated with many-body physics is really infinite in this sort of very precise sense. If we try to scale, many-body qubit problems, or even classical statistical mechanical problems up, even the exact enumeration of the state space is essentially physically impossible. So this motivates us to turn to machine learning methods for some possibly intractable problems, because we know that in machine learning, in industry, images of size 8 by 8 are extremely small. You routinely look at images with millions or more pixels, right? So we know that technology exists that can exploit basically the properties of big data, and this is what we're going to use in this class. Let's review some of the statistical mechanics we need to know in order to basically develop this way of thinking. So the first and most important problem that we'll encounter in machine learning is drawing data sets from a probability distribution, or conversely predicting a probability distribution given a set of data. Okay? It makes a lot of sense in physics and statistical mechanics. You might wonder if it makes as much sense in the machine learning context. You can ask yourself, question, is there a probability distribution of data that underlies an image of a cat? Is there such a thing as a probability distribution that gives me an image of a cat? That's a philosophical question for you. In physics, it's much more clear. So, let's imagine the problem of sort of a system of binary units, an Ising model perhaps, that's in thermal equilibrium with a bath. From statistical mechanics, we know the underlying distribution, and we're going to use it for the rest of the day today, and that's the Boltzmann distribution. So, given some, I'll say, configuration, which I'll be more precise about in a minute, of pixels, or say binary variables, or actually any variable, they don't have to be binary, but I want us to start thinking of Ising spins. And I'm going to call this configuration X, without being more specific right now. We know that the probability of finding a configuration X in nature is related to the energy associated with that configuration. Okay, you should have all seen this before, hopefully. It's a Boltzmann distribution. E of X is the energy. So X is a, say, state of the system. And E of X is its energy. Which we'll define through a Hamiltonian. There's a Boltzmann's constant here, KB, which I'll often set to 1. And Z is the very important normalization factor, which we will encounter lots, or partition function. That applies to physical systems in the canonical ensemble, right? It does not apply to pictures of cats or dogs on the internet. So in physics, we're in this enviable position of actually knowing what we sometimes call the ground truth that underlies a state of the system. That ground truth is the probability distribution under which those states, are distributed. Let me write the partition function for the Boltzmann distribution, by the way. Because the Boltzmann distribution contains this very important object, which is a sum over all possible states of the system, otherwise known as a trace. So the trace is really, for a binary system, to abuse notation, a sum that runs over all possible states of the bits, or the qubits, if you will, from 1 to the size of the state space. Which, I have written a 2 here for binary variables. Right, so the size of the image, or the number of qubits in your quantum computer very drastically affect the computational, if you will, complexity of this normalization. So we'll come back to this several times. So One of the central problems that we will discuss in this class will be the calculation of observable quantities, or what I'll define as expectation values. In the machine learning literature, these are often denoted with this funny E. So let me say expectation value of an observable, to use the quantum language, which you can think of as an operator O. The expectation value is really just the expected value, right? And the expected value in physics, we often write like this. And precisely it's, again, the sum over all possible states in the system, the probability distribution that underlies those states, right? And the value of the observable in each one of those states. So if O is the energy, then if you know the Hamiltonian, right, O of x is the energy of that specific state that occurs in that sum. These expectation values will be quantities that, again, will be central to sort of our discussion as we go forward. One thing we'll be doing is replacing expectation values with supervised learning, right? We'll be, instead of calculating expectation values, we'll be looking at the labels of classifications using neural networks and other classifiers. We can also imagine calculating expectation values in quantum systems that aren't available directly from the data set that we've produced on a quantum computer. These are all applications that we'll encounter throughout the week. By the way, this notation is useful because it translates nicely into quantum mechanics, where I would write the expectation value as some normalization. Let me write this as an operator. Where instead of the trace in that sort of classical sense, I've just written, the partition function in that classical sense, I've just written a normalization here. Right, so the same idea of having an expectation value of an observable translates nicely in quantum mechanics. So we're going to stick with classical binary variables for now, which are just black and white pixels of an image, Ising spins. And let's continue with the example of variables that are distributed according to a Boltzmann distribution. Let's calculate the expectation value of the energy. This is sometimes defined as U in statistical mechanics. Right, as I said, this is 1 over z trace, e to the x, e minus beta e to the x. Right, so by the chain rule, note that this internal energy, this expectation value of the energy, can be written as the partial derivative of the partition function with respect to beta. And let me mention now that this is my partial derivative symbol, not a 2. Okay. This is also the partial derivative of log of z with respect to beta. Okay. Certainly it's something you've probably seen before. From this, you can calculate the expectation value of the specific heat. Okay. This is something we'll calculate, which is, it's defined as the derivative, the partial derivative of the internal energy with respect to the temperature by the chain rule. I can write this as this. Okay, and I know what the expression for beta is. I wrote it over here. It's 1 over kBT. Okay, so I can also write this as or second derivative of log of the partition function with respect to the inverse temperature. This is a 2, and that's not a 2. This expression for the specific heat can be related to the fluctuations of the internal energy away from its mean value. And from this, we will construct one of our first non-trivial expectation values that we'll use in today's tutorial. Okay, so I'm reviewing basically the calculation of sort of standard expectation values in the context of statistical mechanics and thermodynamics. I'll just say from U, from its average value or expected value. So what I'm doing is relating, okay, the specific heat to the mean square. Okay, so the expected squared deviation of, say, the instantaneous energy from its expected value. From the properties of expectation values, you may know that you can write this like this. Just because the expectation value of an expectation value is an expectation value. Okay, that's my proof. In the case of a Boltzmann distribution, the expectation value of the squared energy. So the first term is just written by taking whatever that operator is. O is now E squared, right? And I've plugged it inside my definition of an expectation value for the Boltzmann distribution. And the second term, which I already know the expectation value for, I can write as this. Okay, so I can further refine this by using a similar trick as I used for the internal energy, by just writing this as the square, or sorry, the second partial derivative of the partition function. Let me get rid of this minus 1 squared, which is just 1. And finally, I can write this whole expression as a second partial derivative of log of the partition function with respect to beta. If that step's not obvious, just confirm it with the chain rule. Okay, so now that I have something that looks like a mean squared deviation of the energy, in some sense, that I can relate to the specific heat up to that prefactor, which means that if I write it like this, C over this will be one of our tasks in the tutorial, where we calculate the specific heat. And for those of you that have studied statistical mechanics of phase transitions, you'll know that this quantity diverges at a critical point at a phase transition. And we will see this in our numerical simulations this afternoon. Okay, so that was just a theoretical exercise. What you should be asking, based on the conversation I had on this board in one previous board ago, was how do I calculate these expectation values when they involve sort of the thing I just erased here, this exponential sum. You know, this trace over the, if you will, the size of the Hilbert space that is, you know, growing exponentially with the number of qubits or the number of Ising variables. So that question is, again, central to what we're learning this week in this class. So how do we calculate say these expectation values, whatever they are, in practice? So we're taking a data-driven philosophy because we're interested in machine learning. So one way you can imagine calculating these expectation values is by taking data or drawing data which corresponds to all of these configurations that I've been labeling X from some black box. Okay, from some, you know, physical object that provides basically samples of these configurations. This is sort of the way we would imagine doing expectation values of observables, say for example in a quantum computer, where we can produce projective measurements in the sigma z basis. Okay? That's also how you can imagine you know, parsing through all possible images of cats on the internet and calculating the average, whatever, specific heat of all possible cats. It's a data-driven problem, right? The idea is that this sum here isn't a sum that you calculate necessarily theoretically with knowledge of the underlying distribution. It's a sum that comes from some external source. So we'll look at both of these scenarios. So let's imagine a basic data-driven approach. Okay, so this is maybe something that will look a little bit different than how you are used to thinking about statistical mechanics. And the idea is to estimate the underlying probability distribution of a data set with its frequency distribution. So let's call it a frequency estimate.
So the energy of a particular configuration is easy to determine of a given X.
Correct. Yeah, the question was, can you determine, say, O of X for a given X? And the idea in principle is yes. And we will do this in practice. So that may involve a sum that's of the order of the number of qubits, which we consider tractable, right? It's typically only when these types of sums become exponential that you would start to think of them as intractable. Although that's not a firm, I wouldn't say that's a firm division of computational complexity. So let's look at exactly this question, but let's imagine that we're given now a data set. Again, pictures of cats off the internet or configurations of qubits, you know, drawn from measurements of a quantum computer. Okay, so we're going to introduce some notation. So this data set is a set. X, I'm now being a little bit more precise about what it is. It is, I'm going to call it a vector. And imagine a vector of binary units. So it's a single configuration. For n qubits, or spins. Am I using U? I forget. So, you know, each one of these will be a classical binary variable. For example, 1, 0, 0, blah, 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 1. Right? If you take that vector and you rearrange it, into an image. It might be black, white, white, and this might be your last qubit, which is black. Okay, so the idea is that each one of these vectors in the data set is one image of black and white pixels, or one configuration of binary variables, or so on. We're going to label these K because we're going to draw a large number of these configurations, from whatever the physical object is that's giving us this data. Okay? So the basic data-driven approach to calculating an estimator using data that's given to you by an oracle, let's call it, is to estimate the underlying probability distribution with the frequency of occurrence of each one of the elements of the data set. I'll say approximate distribution. Again, the idea now is that what I was calling P of X before is unknown. So we're going to assume that we don't know the functional form of the Boltzmann distribution or something like that. I don't know, I would say mathematically. But we have an oracle, a computer, a hard drive full of cat pictures or something that we can basically draw samples from that distribution from. Okay? I'm going to call that small p of x. And that's defined via a normalized sum. So that's 1 over size of the data set x of k in the data set delta x of k. This is the frequency estimate for that distribution. All it means is, like, if I want to know the probability of a particularly nice looking cat picture, I just look at how many times it occurred in that data set. And if that particularly nice cat picture is the ferromagnetic state of an Ising model, or I don't know, the error correcting regime of a topological qubit or something, it's the same point. I look at the distribution, so the sum over all of these elements that occur in the data set, and I have one count for every time it occurs. So you're building a histogram, and we'll talk more about that histogram and whether or not it's useful. But let's just assume that it's a good representation of the underlying probability distribution for now. We can define an estimator, which is it's an estimate in the way that this is an estimate. So it's an estimator for an expectation value. Okay. Where okay, so let me write the expectation value again. So I'll do it in the Boltzmann distribution, Matt, remember, or sorry, I'll just do it in any classical distribution. This is big P of x, but this is unknown mathematically. Okay, so let's just assume it's unknown. And let's substitute in small p of x, which is the approximate frequency distribution. So this notation means size of the data set. Again, I'm just substituting in. Do I have vector signs there? Yes. Here is my O that I assume I can perform a tractable calculation on. That's a good point, because if this is something that contains a trace within it, or something that is like a density matrix, or like a entanglement entropy or something like that, oftentimes this is not a tractable estimate. So we have a sum here, which is over the whole complete size of the Hilbert space, right? I have another sum here that has a delta function that only picks out elements of the Hilbert space that occur in the data set. So I can collapse those two into just that single sum, which is a subset, if you will, of the Hilbert space. So another way of writing the estimator is just x, okay. Just the, say, energy, specific heat, whatever it is that you can calculate on the elements of the data set, right? Each one of these is a very concrete set of data given to you by, you know, all those pictures of cats you have on your hard drive. So again, this is only exact basically when, you know, this sum covers the entire Hilbert space is one way of thinking about it. Or alternatively, when the data set becomes infinitely large. Assuming that that data has been drawn from the underlying distribution. That's important, right? In order for this to work, each one of those elements of that data set have to be drawn from the unknown distribution that exists somewhere, say, in a quantum computer. So this is important because we're often dealing with very finite sized data sets. This is true in machine learning and in physics. So finite sized data sets. But I don't know what kind of equation I'm writing here. You know, the Hilbert space, as I argued, is exponentially large. So the number of possible states that you're drawing from is very, very large. But you know, your computer can only handle some finite number. So the reconciliation of those two facts is basically one of the big strengths of machine learning. How do you get a good approximation for a probability distribution when you only have a finite data sets? So we'll struggle with this as the week progresses. So that's the question of generalization. So we often talk about generalization in machine learning. You only have, I know it might not seem like it by looking at your phone, but you only have so many pictures of cats on there. How do you infer the correct probability distribution from that relatively limited size data set?
Roger, I got a question.
I'm listening.
Put it in the context of, I don't know, quantum information. You have an experiment or a source of photons, and you don't know the specific state that that source produce, so you don't know that P of X, right?
Right.
So you don't want to do tomography, but you want to do some experiments, and
right.
From those experiments you can calculate those estimators without doing the tomography, the whole tomography of the state.
That's one thing we'll talk about, right? So that's one goal of this type of machine learning, is to do approximate tomography on finite size or finite numbers of, say, resources on limited data sets. And it might not always be possible, right? The tomography problem itself could be exponentially difficult based on the structure of the wave function. But there are wave functions, which are just generalizations of this, right? Complex generalizations of probability distributions, that it is possible that finite sized data sets and finite computational resources may give us a good reconstruction. Yeah. So again, that's I think one of the themes of what we're trying to do here is sort of reasonable, you know, reconstructions of states, and I'm thinking of this as a state now, using again finite resources and maybe even probing when that's possible. Any other questions? We're going to come back to this frequency estimate sort of expression for the observable or the estimator. This should be an approximate sign here. That's your estimate. Right? Yeah. Because I've substituted in P, big P for small p. So we're going to come back to this in the second half of this lecture in the context of Monte Carlo simulations. Just before, we're going to take a break, because I know you guys have been sitting around for a while. I just want to sort of motivate the problem that we're going to look at a bit more today in terms of, moving past just sort of abstract theory and looking a little bit more at what the data is that we're looking at and what is the probability distribution. So let's get concrete. So what do we want? We want, x, say, and p of x. Okay, so we'll consider the Ising model. Which is binary variables, as I mentioned over here. Instead of x's, I'm going to call them sigma z's, or if I forget the z, it's just going to be a sigma, which is -1 or +1. Okay, so you have to map. Maybe this is a +1 and this is a -1. You'll encounter this maybe when you do some of the tutorials. But I'm writing it like this so that we can write the standard Ising Hamiltonian. Okay, and I'm writing it as H, so I can imagine generalizing this to a quantum Hamiltonian. But in this case, this is just really, the energy. And what I've done here is I've summed over all nearest neighbors. So this is all nearest neighbors. And I'm going to consider a two-dimensional lattice. Which gives us a nice mapping between, sort of this physical system and images. So I'm imagining Ising variables on the vertices. So maybe this is a +1 and no dot is a -1. Blank equals -1. And I want periodic boundary conditions. Periodic boundaries mean that when I come to the edge of my lattice, this bond here connects to this site, and so on. This bond here connects to this site. Okay, so this whole thing's a torus. What that does is it reduces finite size effects on the physical estimators that we're going to calculate, which are like the energy, the specific heat. We'll calculate the magnetization and so on. So the probability distribution P of x, in this case, again, is just given by the Boltzmann distribution. And the partition function, again, just to beat a dead horse, is the trace over all possible values of these binary variables. So here's sigma n for n qubits, right? E to the minus beta h. And sometimes I've just been writing this as a sum over x, but basically that's the same idea as sum over sigma, say e to the minus beta. It's really the set of all sigmas. I don't know, e to the minus h. And of course, h depends on the values of sigmas through this. That trace is your, again, exponentially complex object. Okay? So what we're going to do is we're going to study estimates or estimators for how to approximate that trace and calculate physical observables in the context of this model.
How do you physically make an Ising model?
How do you physically make one? Ising models exist in systems in nature, in condensed matter systems, where this type of Hamiltonian just describes the interaction between magnetic moments. So it's sort of an abstract or an abstraction of some physical processes. People can also make synthetic Ising models. They can fabricate them in things like FPGAs and so on. So they can occur in nature, in materials, but they can also occur in devices that you make, right? And again, you can think of it as a classical limit of a qubit quantum computer. For example, the D-wave quantum computer that you might have heard about is just this Ising model plus a transverse magnetic field, which is a field in the sigma x direction. That transverse field can be shut off, and then the D-wave Hamiltonian is just described by an Ising model. Maybe not a nearest neighbor Ising model, but some sort of Ising model. But I think more importantly, an Ising model is really, it's sort of the, it's sort of the test bed for a lot of the concepts that we need to sort of flesh out when we're talking about these many-body systems. Right, so the ideas of traces in partition functions, the ideas of having many interacting, in this case, classical bits. If we can't sort of understand how to do things like calculate physical estimators in these classical models, then it's basically hopeless to think that we can do so in quantum models. So this is, in my perspective, sort of the important first step in building up a toolbox to work more generally on quantum systems. Let's take a break until 1:45, okay? Sorry?
Is it possible to take a break, like, let's say like 10 minutes, because
Sure.
coffee's almost ready, and then we can...
Oh, then we can squish the coffee break into... Okay, let's do that. Stay in your seats. So, I'll go till 1:45. And then, sorry, what after the coffee break?
So,
how much time will I have then?
well, you'll have... so we can do a half an hour coffee break,
Uh-huh.
and then we can... I mean, you still have like your 2 lectures.
Uh-huh, so... Okay, I'm going to move on to the second lecture now. I'm going to start the second half now then. Just so we don't go too long. This lecture is, how do we calculate this estimator? And this is what you're going to do in the tutorial. When I motivated this estimator here, I told you that the data set was drawn from some sort of oracle, some sort of computer, your hard drive, whatever. What we're going to talk about now is a way to produce a data set, okay, given knowledge of the underlying probability distribution. So it's kind of the opposite problem. But the techniques that we learn when we discuss these types of simulation methods for producing data are used in many different applications, not only in statistical mechanics and physics, but also in machine learning algorithms. So these Monte Carlo simulations are actually going to be used quite extensively in Thursday's lectures when we discuss restricted Boltzmann machines. Okay. So this is a numerical way to calculate, say, some expectation value or an estimator for an expectation value, given some knowledge of a probability distribution. And these are also widely used in machine learning algorithms, particularly those that have any sort of sampling stage, like, for example, the restricted Boltzmann machines of Thursday. Okay, so we have more than one reason for studying Monte Carlo simulations in this class. So again, the philosophy is to produce this data set. Did I delete it? Erase it? Yeah. Okay, that's distributed according to some distribution, big P, where each x of k is whatever xn. In your tutorial, what you're imagining is a two-dimensional lattice of these variables, plus and minus 1, or whatever you want to call them, zeros and ones. And what you're doing is you're imagining producing that data set using a simulation method. Once you have that data set, then you can calculate an estimator using this method, which you will do. Okay? So then the goal is to use that data set to estimate. So Markov chain Monte Carlo answers the question of how do you produce a data set that's distributed correctly according to that probability distribution Q. And the most important, I think, lesson of Monte Carlo simulation is that you do not produce a data set simply by random sampling. So probably many of you have seen Monte Carlo simulations before. They're often introduced as, if you can calculate an estimator by drawing random samples, then each one of those random samples, I think I just deleted or erased it. You multiply the probability distribution by, whatever the expectation value in that random sample. That gives you your expectation value, your observable. In Monte Carlo simulations, what you're trying to do is essentially produce a data set that's correctly distributed according to that underlying probability distribution. That's called importance sampling. Random sampling implies sampling of a number of configurations that's exponentially large due to the Hilbert space. Bad. Due to the n. Importance sampling. So yes, importance sampling. Which basically means that if you have some distribution, P of x, you preferably draw samples close to the peak in that distribution. So you might draw many samples here. You might draw a few samples out at the tail. And you should basically draw no samples, out where the distribution has no weight. That's just kind of the idea of importance sampling, and it's mathematically equivalent to the way that we define the frequency estimate. So the idea is to start with some maybe random configuration. So that's x1. So it's your first, if you will, image, For the Ising model, you might pick some random ups and downs. And the idea is to use that starting image to produce a chain of subsequent, if you will, images or configurations. So modify. So Monte Carlo means to modify or update configurations in a chain. So you might start with x1. There's some update procedure that gives you x2, so on, x, all the way to x, which is the size of the data set, right? The important thing about Monte Carlo updates, so each one of these is sort of your update. It might be, flipping a spin, or it might be flipping a cluster of spins, is that each new configuration only depends on the configuration before it. That's the definition of a Markov chain. Which often gives the name Markov chain Monte Carlo to this type of procedure. Okay. And then this thing here is your data set. The Markov chain thus produced is D. You can imagine storing D to your hard drive and using it later to calculate estimators, giving it to somebody else, and for them it's just a data set that's produced by an oracle. Or you can imagine calculating estimators in real time as you're doing the updates and then throwing away the configurations. And sort of what's implicit in this discussion is the idea that the number of samples produced, or the number of samples required in order to produce an estimator is less than this number here, right? So you're hoping that somehow by this procedure, by focusing on samples that are correctly distributed with the underlying distribution, that you're avoiding sort of the exponential overhead of the full sum in the trace. So what we need to do to design a Monte Carlo procedure is to essentially design these arrows. How do I start from a random configuration or a random image of Ising spins, and how do I propose updates that are distributed correctly according to this distribution? Yeah, for us it'll be the Boltzmann distribution. So we're going to assume that we know that. Okay? So let's explore that after I have coffee.